So we are concerned about a function on the closed interval AB. The function is real valued and finite valued. We don't allow the function to be equal to infinity. So first, let us define a partition. A partition of this closed interval AB, if you may recall, is just a sequence of points in that interval AB written in increasing order. So we write down A as our x0, and B is our xm, and then the other x's, x1, x2, x3, are all written in increasing order. As always, you can think of a partition as a way to divide the closed interval AB into several smaller subintervals. So first, let us introduce this variation sum along the partition P. So if you have a function like that and you have a partition on the interval, we can define a variation sum. So we take the sum of f of x1 minus fx0, f of x2 minus fx1, f of x3 minus fx2, all the way to f of xm minus f of xm minus 1. And keep in mind that we are taking the absolute values. So these are just sums of positive numbers or non-negative numbers. So this variation sum speaks to the total vertical travel of the values fx0, fx1. So basically, if you have a point going from fx0 to fx1 to fx2 to fx3, fx4, what is the total distance thus it travels vertically? Of course, when you have a different partition, the vertical travel that you measure is also different. Okay. So we want to figure out what is the largest amount of vertical travel that the function's graph can go through. And this is what the variation is. So we define a variation as a function that takes as an input the function f and the interval AB. And it's the soup of all the possible variation sums that you get from these different partitions. Okay, so every partition will give you a different measurement of the vertical travel of your graph. And the variation is just the supremum of that. Now, the main topic of this first lesson, we say that f is bounded variation if this v is finite, and it is unbounded variation if the v is infinite. So one observation is in connection to refinements of partitions. So if you may remember, we refine a partition by adding more points into the interval. If we refine a partition so that we cut up the subintervals into even smaller subintervals, this cannot increase the variation sum, cannot decrease the variation sum, sorry. This is due to the triangle inequality. Right? If you add a new point in the middle by the triangle inequality, the distance from fxi to fxi minus 1 has to be less than fy minus fx minus 1 plus fxi minus fy. Right? This is just an application of the triangle inequality. So this means that your variation sum here, if you add an extra point into your partition, can not decrease. It can only increase or stay the same. Now, let's first clarify this concept with a few examples. So I know that the definition can look a little bit scary, but I think once you've seen a few examples, it doesn't look that bad. Now, let's just consider a monotone function. A monotone means that the function never decreases or never increases. Let's just consider an increasing function. The function is always just going up. So if you consider any partition P on the interval AB, so since the function is always going up, always increasing, fxi is always going to be larger than fxi minus 1. Okay, so this means that when we look at the definition of this variation sum, we can ignore the absolute values because fxi minus fxi minus 1 is always going to be non-negative anyway. So we can just remove all the absolute values. But observe what happens when we do that. When we do that, all the terms cancel except the first and the last term. So you may notice that you have fxi minus fxi minus 1, but then you also have, okay, we start with, let's say, fx1 minus fx0. Then we have fx2 minus fx1, fx3 minus fx2. But you see that the fx1 cancels out, the fx2 cancels out, fx3 cancels out, and all that you have remaining is the last term and the first term. So you only have fxm minus fx0. But of course, xm is b, x0 is a, and we're left with just fb minus fa, which means the value of the function at the last point minus the value of the function at that first point, right? And this is a concept that we call a telescoping sum. If we have a decreasing function, it remains the same. Now, what happens now is that the absolute value changes everything to a negative, right? But we still end up with the same thing. Okay, we still end up with the same thing, and we end up with fa minus fb instead. So every monotone function will have bounded variation, and the variation will be exactly the absolute value of fb minus fa. So if the function is increasing, you get fb minus fa. If the function is decreasing, you get fa minus fb. So because the monotone function will never reverse the direction, if you look at how the graph travels vertically, it only ever goes up or only ever goes down. So the variation is just the difference between the starting value and the ending value. So let's look at a picture. So here I have the function fx equals x squared plus 1 on the interval 0, 3. So here a is 0 and b is 3. So the function is always just going up. So if you look at the vertical distance that it travels, it is just going to be exactly 9, right? 10 minus 1 equals to 9. Okay, and it doesn't matter how you cut up the interval 0, 3. You can partition 0, 3, you can cut 0, 3 into smaller pieces however you want. But at the end, the distance that the vertical distance that your graph travels in will always be 9. It doesn't matter which partition you choose. So let's try another example, and this one is a bit less simple. Now, let's say that we have a function that consists of monotone arcs. So it can go up and then go down and go up and go down and go up and go down, right? So here's how we define it. We start a equals a1, b equals ak plus 1. And between each of these a1, a2, a3, the function is either increasing or decreasing. So it goes up and down and up and down and up and down. Okay, and it turns out that the total variation is still going to be, like, the total variation is going to be like this. So you look at the increasing part, the next decreasing part, the increasing part and decreasing part. You look at the points where it increases and decreases. You look at the endpoints, and then you take the difference. Okay. I think we're not going to prove this. I think it's going to be quite straightforward to prove, but I'll just go through an example. So let's say a function f goes from 1 to 4, and it goes down to -2 and up to 3 again. Then the variation will just be 4 minus 1. The increase from 1 to 4 is 3. The decrease from 4 to -2 is 6. The increase from -2 to 3 is 5. So you get 3 plus 6 plus 5, which gives you a variation of 14. And again, you will get this variation no matter which partition you choose, right? All right, so let's look at the picture. Okay, so again, you see that as the function goes from 0 to 4, right? So this, okay, so I didn't give down the function's formula here, but the function goes from 1 to 4, you get 3. From 4 to 2, you get 6. From 2 to 3, you get 5. So you add them up together, you get 3 plus 6 plus 5, which gives you a variation of 14. So again, it doesn't matter what partition you choose, you will always get the same answer. Now let's try a more interesting example. This is the Dirichlet function that we saw a lot of in your analysis class. So again, we just define for the interval AB, your function f will be equal to 1 if the input is a rational number. Your function f will be equal to 0 if your input is an irrational number. So you don't forget that every interval contains infinitely many rational numbers and infinitely many irrational numbers. All right, that's the concept of density. But that means when we choose our partition, we can choose it in such a way, for example, that all the odd points, x1, x3, x5, x7, are irrational, and all the even points, x2, x4, x6 are rational. We don't count x0 and xn in that, and then the last one in that. So we can choose it so that you get rational, irrational, rational, irrational, rational, irrational, rational, irrational. So the Fs will alternate between 0, 1, 0, 1, 0, 1, 0, 1. And that means that your partition will have n-1 jumps of size 1. So when that happens, you get, at least, there could be more, right? N-1 jumps of size 1. So it means that when you calculate the vertical travel of F on the partition points, it will be at least n-1, okay? And big N can be any number we want. So don't forget, for our partition, we can include as many points as we want, as long as the number of points is finite, okay? So that means that our SP, our variation sum, that depends on the partition, can be bigger or equal to big N-1, where big N can be any positive integer, right? So let's again look at the definition of variation. The variation is the supremum of all these SPs, right? The variation is the supremum of all these SPs. But we know that the SPs, you can find an SP that is larger than any positive integer. So it's unbounded above. It's not bounded. You can find SPs that are as large as you like. So when you take the supremum of all the SPs, the result you get is just infinity, right? And indeed, we find that the supremum, that the variation of this function will be positive infinity. Let's go through another example. Okay, this is again a concept that we've learned in our analysis class, that of a Lipschitz function. A function f is Lipschitz if there is a constant c known as the Lipschitz constant, so that the distance between fx minus fy is less than or equal to c times the distance between x minus y for any xy in your domain interval. So this means that for any partition P, if you pick any partition, then when you calculate this variation sum, it's going to be less than or equal to c times the distance of the points. So you have, again, x1 minus x0, x2 minus x1, x3 minus x2, and we have the same telescoping cancellation. We end up with c times xm minus c times x0. So again, xm is b, x0 is a, so it's just c times b minus a, right? This is, oh, okay, so it's not equal, it's going to be less than or equal to. That's the Lipschitz condition is less than or equal to, all right? So of course, we don't exactly know what the variation sum is, so we can't tell what the variation is, but since all the variation sums are less than or equal to c b minus a, when we take the soup, so don't forget, the variation is just the soup of all these SPs, but if all the SPs are less than c times b minus a, the soup must also be less than or equal to c b minus a, which is a finite number, right? So this means that our Lipschitz function is of bounded variation as well.